Hi, everyone, and thanks for joining. I am Miroslav Lžičar, CTO of DeepMedChem, and today I'm here with Krzysztof Stach, our application scientist and medicinal chemist. And I'm going to introduce SynthonGPT, our approach for molecular search in extremely large synthon-based chemical spaces. The main idea is that we can search and generate across spaces on the order of tens of trillions of molecules, while still staying grounded in real synthons, real reactions, and practical synthesizability. I will first explain what does this mean, then talk about the model itself, and then some interesting use cases or case studies such as chemical space sampling, reinforcement learning, or substructure search. Let me start by contrasting enumerative and combinatorial chemical spaces. Enumerative spaces are basically lists of molecules, which can be more or less arbitrary, and usually you don't enumerate more than billions of molecules. Currently in CHEESE, we have 16 enumerative databases which support more than 40 billion molecules. And synthon-based chemical spaces are instead defined by some rules like reactions and building blocks you can use to synthesize products. And this means that they can be orders of magnitude larger because just by millions of synthons and so a few reactions, you can already get to multi-trillion chemical spaces. Currently, we support 6 such databases and more than a trillion of molecules. This also means that the synthesizability is very straightforward because all of these virtual libraries have like orderable chemistry you can purchase and have in a few weeks synthesized with a high success rate. And all those like synthons are defined, so there are like no hallucinations or headaches with retrosynthesis. And SynthonGPT is a generative model which focuses on these combinatorial or synthon-based libraries. It analyzes the query compound on the level of the synthons from which it can be synthesized, and searches in all these virtual libraries like enamine, e-molecules, ChemSpace, XTALPy, or Molecule 1, where you can actually order the products it generates. And this is very, very practical, and in most of or in a lot of virtual screening programs, you usually start by screening one of these libraries and then ordering the compounds to test them. SynthonGPT is an autoregressive transformer architecture which we built and trained in-house on these databases. And it is distinct by its retrieval-based decoder, which is grounded in the synthons from these libraries. You can actually specify and thus it is not any sort of text generation or classical GPT because everything it generates, it actually needs to draw from these predefined synthons. So it cannot hallucinate some nonsense. It is always like grounded in what synthons or building blocks and reactions you specify. And if you have the correct definition of the chemical space, then you will also have correct products or correctly generated compounds from this model. And thanks to this architecture, it is able to either search based on a query molecule when you need to find similar to some compound you already have, for instance, in a hit expansion or other cases. Or you can generate new molecules existing in the synthon spaces from scratch, perhaps to use it as a generative optimizer and optimize some like compounds which actually exist in those chemical spaces. In comparison with state-of-the-art synthon search, there are already some industry standard tools which are non-AI but widely used in cases where you need to search virtual libraries, and mainly it's F-trees and Spacelight, which use either the tree algorithms or some fingerprint-based synthon topological synthon retrieval to find the most similar compounds existing in synthon spaces. And we did a benchmark here where we searched the same set of compounds on the same chemical space, in this case freedom from ChemSpace, do it 100 times and record the Tanimoto similarities of the molecules we found, as well as unique Bemis-Murko scaffolds. And we observed that CHEESE SynthonGPT is very competitive in terms of the diversity of the hits, because it has the lowest Tanimoto similarity to the query, and also the most unique Bemis-Murko scaffolds, almost 3 times as much as F-trees, which is well known for its ability to scaffold hop or come up with diverse molecules. So this means that the generative model didn't overfit, and instead learned to sample like very diverse molecules, and in some cases even beat these very strong traditional techniques. This translates directly also to the uniqueness or novelty of the compounds that SynthonGPT can search or generate, because in this case, while F-trees and Spacelight compounds slightly overlap, SynthonGPT did not, and all the molecules were unique. So from these benchmarks, we can conclude that at least SynthonGPT is complementary or comes up with compounds that other techniques can miss. And on the other side of the spectrum, we have state-of-the-art generative models in the recent literature, such as Prexin, Riacin, Synformer, or Synflonet, which are usually trained specifically for retrosynthesis or chemical space search or optimization, optimization and reinforcement learning, where you are generating some molecules and then want to optimize certain properties or docking scores or affinities. So and from this literature, the strongest and the most recent model so far is Prexin from Conor and Shiton Kluo from this paper, and it is as well the decoder-based transformer in GPT style, similarly to SynthonGPT, and it beats all these prior models. So let's talk about what are the similarities and what are the differences, and how do we compare. In contrast to Prexin, our main advantage is the practical usability, because Prexin is very performant, but it's restricted only to the single database it was trained on, specifically on enamine. And if you have some update of the database or want to use it on different database, you would need to retrain this transformer from scratch, which is very expensive. Whereas in case of SynthonGPT, it's trained once on multiple databases, and it supports simple updates or addition of new databases it wasn't trained on, and it is not needed to retrain the transformer. Also in contrast to Prexin, where the synthesizability of the molecules it generates isn't always guaranteed, we are restricted to 6 progressible chemical spaces, like as I said, chem space, simple, and so on, where we work as well with the Synthon-based format, and not just with the raw building blocks interactions. And you can then send the IDs of the molecules from SynthonGPT to the vendor, and he will send you those compounds, and it will be valid molecules existing in these databases. The only like exception in our case is enamine, where we are still aligning with the vendor chemical space, but in all the other cases, it's guaranteed to be orderable and without hallucinations. So this is the main difference, and that's because SynthonGPT is retrieval-based, has retrieval-based decoder, where it doesn't just generate probabilities of the individual syntons or building blocks, but always retrieves them by using some representation of the molecule. So if you add more syntons, you can do it, and this means that it will also scale much better. For instance, if you have 10 times as much syntons, you would need 10 times bigger Prexin model, but with SynthonGPT, you just have 10 times bigger synton index, and you don't need a bigger or more parameter model. So this is also another advantage. And more things are that we support as well a substructure search natively in the decoder or smart pattern filters, and SynthonGPT is as well faster. What SynthonGPT doesn't have and Prexin has is property-based prompt conditioning. In Prexin, you can add some properties or constraints into the prompt, and then the model is conditioned to retrieve molecules satisfying the given properties you want. And Prexin also might be better suitable for retrosynthesis because it was trained on the raw building blocks, and also it was trained for longer chains of more steps of retrosynthesis. But as I said, in SynthonGPT, we can guarantee that the molecules are orderable from these vendor virtual libraries, whereas Prexin has a custom version of a database which isn't orderable anywhere, and you would need to still figure out how to synthesize the molecules. Then let me talk a bit about a very nice use case, which is chemical space sampling or active learning. The task is basically to use SynthonGPT not just for search, but for retrieving optimal set of molecules from these chemical spaces based on what you want to optimize. And usually the goal can be, for instance, to get the best docking molecules with minimum compute, because you don't want to dock trillions of compounds. You want to dock just thousands or maybe millions and get and converge towards the best from molecules from the virtual library, even with just a fraction of the time and compute spent. And more generally, this is usually some task of multi-property set optimization, because in practical scenarios, you don't want just best scores, but also to have diverse set of compounds, to have the compounds satisfy some ADME properties or some predicted activity based on empirical measurements, and so on and so on. So there can be multiple properties of this set of molecules you want to generate to optimize. And yeah, here is some visualization taken from multiple paper, where you can see the contrast of the brute force docking chemical space versus doing some sort of active learning or some procedure of sampling some molecules, training a model, then docking them, then updating the model based on the results, and so on and so on. And this is very efficient, and by some loop like this, you can usually achieve huge enrichment with fraction of compute. And the chemical space sampling is some idea like this, so how to optimally sample molecules from the chemical space to achieve maximum with minimum compute. It's worth mentioning also two recent strong baseline in this field. One is Thompson sampling from Patrick Walters and others, where it works with Synthon-based libraries by scoring which Synthons perform well and then sampling them more often. And on the right side, we have Space Hasten, which is kind of iterative search, where you always search molecules, dock them, and then take the best, search them again, and this way you can iteratively improve the docking scores a lot. And we did some first experiments in this regard with SynthonGPT, using it as a generative model to do chemical space sampling. And in this case, we focused on docking score proxy, which means docking score predicted by a surrogate model on KIF 11 plus maximization of the diversity of the predicted set of compounds. So it was on freedom space. The goal was to select top 1,000 molecules, but with docking just 10,000 of compounds maximum. And there is the orange dot on the top, those are the top 1,000 molecule with the best docking score, but slightly lower diversity, because it's how these chemical spaces usually are. And then there is the green line is a Pareto front of these are sets of molecules with the maximum diversity for the given mean docking score. So this is the optimal ground truth you want to achieve. And the purple dot on the bottom, that's just a baseline approach where you sample 10,000 compounds randomly and then take the top 1,000 best based on docking score from them. So that's basically just like one iteration. And then we have here the Thomson sampling, which achieves like a huge improvement in the diversity as well as docking score. And on the right and on the left, these are different algorithms paired with SynthonGPT. One is the iterative search expansion, the ICE, that achieved better docking score than Thomson sampling, but a bit lower diversity. And on the right, we have reinforcement learning using fine-tuning, supervised fine-tuning approach, and that achieved higher diversity than Thomson sampling, but lower docking score. So these are some first experiments where we are trying to push this Pareto frontier of the diversity and optimization, docking score optimization. Yeah, here is it explained again what the abbreviations mean. And here's another look at it in terms of the distributions, where on the left, on the x-axis, we have docking scores. So the more to the right, the better. And on the left, there's the distribution of the random top 1,000 baseline. And you can see that the distribution of the docking score for the SynthonGPT with iterative search expansion is the best and overlapping with the Thomson sampling baseline. We have tried also proximal policy optimization, which is reinforcement learning used a lot in NLP and in ChatGPT as well. However, this technique managed to increase the scores over time. You can see it in the curve on the right, where there is the number of steps on the x-axis, and it increases throughout this optimization. However, we always struggled with a mode collapse, basically collapse of the diversity. So whereas this may work in some cases, it usually collapses to just one chemotype or one set of compounds, and thus cannot compete with the other baselines.
Perfect. Now it's my time. So as I said, I will now guide you through the practical aspects and applications of CHEESE SynthonGPT, which can be accessed via our user interface. And the whole search for the molecule can be commenced by writing your smiles of your molecule of interest, or drawing the exact structure into the editor, and then searched via the button here on the right upper corner, where you enter actually the search interface when you have to search Synthon search, which will direct you to the non-enumerated chemical space composed of databases within this CHEESE SynthonGPT module. And one of three options how to search our molecule or your molecule is via the similarity search, which will analyze the molecule based on the single synthons which the molecule is composed of, and search for these single synthons within the selected database, one of our 6 actually, which in total gave, as Miroslav mentioned, 40 plus trillion of compounds. So then these synthons, when they are searched for, are assembled back together to the molecule, resulting molecule, via the combinatorial approach, so which results in the selection of the generation of novel molecules bearing different structural scaffolds, however retaining the same structural features as the query molecule. Once you select all your options, here the synthon search, similarity search, and database of your choice. It can be one, two, or all of them. You can then proceed to the results. The search itself takes merely seconds, as it's very fast. Here, on the next step, you can see examples of searched molecules, the resulting molecules. As you can see here, the query molecule and the resulting molecule are somewhat similar. However, they bear different structural features, which is exactly the thing we wanted to achieve, to expand the library from the combinatorial aspect, or from the perspective of the combinatorial approach. However, retain the structural similarity with different scaffolds. You can also limit the resulting molecules using properties filters, where you can search, for example, for the similarities, for different ADME properties, filter via the mass filter, another properties such as log D, log P, etc. Our newest asset, which is not implemented only in CHEESE SynthonGPT, but as well as in CHEESE Search, is the partial charges and conformal alignment, which actually in the first case shows you the partial charges of every single atom in your selected molecules, and the conformal alignment shows you how your molecule of selection actually aligns with the query molecule that you input to the query as a query at the very beginning of your search, which can be a very useful tool for comparison of your resulting molecules and further studies. In the next step, you can also check from which synthons your resulting molecules compose of, and eventually buy them via our vendors or our collaborating vendors. But this is sort of a retrosynthetic approach to see actually which synthons from our databases were used for the generation of your resulting molecules. Also, this is an example of the substructure search, where we are analyzing the query molecules on the level of single synthons, and actually providing those synthons from our databases, and which can be used, for example, for the approaches involving structural-based virtual screenings, where you can really download single synthons from the query molecule and use them in your pipelines in order to analyze, for example, the binding properties of your molecules of your molecule from the perspective of single fragments, or to use it to overcome some patent protections, which is a very frequent demand from our customers. The third approach towards this CHEESE SynthonGPT application from the perspective of the search is search of superstructures, which actually stabilizes the query molecule within the structure of the resulting molecules, and then tries to decorate the selected scaffold in very rich plethora of ways, and in order to get some structural diversity regarding to your starting structure or the query molecule, and thus it uses the query molecule as the core of the resulting structures. You can also use some smart filters in order to implement the structure that you desire to be present in your structure. In this case, it is 1,2 diol, which is, as you can see, present in all of these resulting structures. This enables you to actually fix your core molecule within the resulting ones, and as well add some filters on top of the resulting structures, which limits the structures exactly in the way how you want. You can exclude these smart filters as well as exclude them. So, for example, if there is any structural feature that you do not desire to have in your structure, you can just simply exclude it, and you are 100% sure that in the dataset this motif is not present. One thing also worth mentioning is that you can generate 100 molecules, 1,000 or 10,000, and then directly download them and use them in the pipeline that you are using. You can download them in the CSV files, in the JSON, or any standard data file that is usually used for such pipelines. This is the part where I'm going to start talking about some practical use cases. The first one of these actually continues a little bit a talk about the space hasten, which was mentioned by Miroslav, where we applied the CHEESE SynthonGPT together with our collaborator as a tool for iterative hit expansion of the docking of the compound that resulted from a docking study. The whole study started with the selection of 100,000 compounds from the seed database, which was ChemSpace. And in the first step, or the 0th step of the experiment, we performed a docking. Then we selected 100 best compounds from this docking and used CHEESE SynthonGPT to expand this library of 100 compounds. We actually generated 10,000 compounds per query, which gave us 1 million compounds in total in return to analyze further. So in the next step, we repeated the whole process using this space hasten algorithm. We evaluated the activity of all of the whole 1 million membered set, selected 100 best molecules, and repeated the cycle with the expansion using CHEESE SynthonGPT and evaluation 3 times in total. In the end, we performed a final docking study, which actually resulted in a very positive result, where initially we started with something about 16 virtual hits. The final result gave more than 700 virtual hits that seemed to be very interesting towards the target. Also, we in general aim on the very high customizability of our technology, and CHEESE SynthonGPT is no exception. Actually, the user or the client collaborator can input his own reactions, his own building blocks, in order to actually search the desired chemical space that, in some cases, is not present in our databases, although they are quite very large. Some building blocks and reactions are not present yet. So we offer the full customizability to our partners, where they can input their own reactions, define their own reactions, and define their own chemical spaces. In one case that we did quite recently, we did perform a short study where the client did ask us whether the CHEESE SynthonGPT would be useful for generation of novel non-canonical peptides. And he gave us a short sequence that he wanted to iteratively expand in order to use non-canonical amino acid and achieve better diversity and better affinities towards this target. And in another case, another client did ask us if it would be possible to actually implement reactions into CHEESE SynthonGPT in order to actually achieve these tricyclic heterocycles, which are supposed to be derivatives of certain kinase inhibitors. And it's possible very easily actually to create such demonstration, or such proof of concept, when we retroanalytically retrosynthetically analyzed the molecule of interest and then searched for the respective building blocks which composes this starting, or the crucial building block. And actually we defined the reaction. So the first step was the synthesization of the query molecule, and then search for the respective syntons, and then molecule assembly, applying our defined reactions. And in a very short time, we were able to actually customize the function of CHEESE SynthonGPT in order to get more than 54,000 unique molecules that were structurally close to the query molecule, and thus fulfilling the wish of our client in order to say customize the module in order to give him specific reactions he wanted to get. In the case of unnatural peptide generation, the approach was similar. We analyzed the peptide on the level of single synthons, in this case on the level of amino acids, and searched through our databases in order to actually find structurally close amino acids, and then assembled these, in this case, tetrapeptides together in order to get a rich variety of structurally close peptides that were resembling structurally the query structure. However, they were structurally different. This approach was then applied in a similar case, which was actually building on top of this one, where we took the antimicrobial peptide BAC7 and used CHEESE SynthonGPT to iteratively change the sequence or the amino acids in positions 18, 19, and 20 in order to increase the activity of the set peptide. We used the library of 20 canonical amino acids together with a large variety of non-canonical amino acids from the library, which in total give almost 70,000 combinations that could be used for this modification. And in the end, we were able to generate a variety of novel peptides where many of them actually showed very interesting predicted properties that were actually more favorable than the benchmark starting protein. We used many non-natural or D-amino acids in order to iteratively approach this problem, and which is a showcase that this CHEESE SynthonGPT can be used not only for the generation of small molecules, but for also larger ones, as peptides are, as it can be very easily customized towards the target, towards the client's desire. Yes, and this is the conclusion of our webinar. If you are interested in the CHEESE SynthonGPT, you can try our 14-day trial, which you can find on our website. And you can find the recording of this webinar or any previous one on our YouTube channel. And if you are interested more into the technical part of CHEESE SynthonGPT, you can also read the report on SynthonGPT on our blog. So thank you so much for your attention.
Thank you too. Thanks, Christopher. Let's make a space for comments and questions. So if you have any questions, now is the time to ask. You can write them in the event post or in the comment section. And yeah, let's give a few minutes to it if there are any. Oh, great. I see already a first question from one user who is asking, can you implement pharmacophore features into the workflow? So, Christopher, you can maybe answer.
Yes, that is possible. Actually, in the next iteration, we are going to expand the smarts library, or actually to enable actually inputting your own smarts to the SynthonGPT search. Therefore, then you could also define actually specific pharmacophores or specific features that you want there. So at this point, the limitation on some filters is only led by those filters that we predefine, but in the next iteration, it will be possible as well to add your own pharmacophoric features that which you want to your compound actually to have.
Thanks. You can also let us know in the comments if you mean pharmacophore search in general or in some like specific pharmacophore features, which based on the pattern filters, maybe some of them are already there. Oh, and I see already additional comment. I was looking about the 3D pH4 like in MOI. So these like 3D pharmacophore features, yeah, that's like another topic. Or I should probably mention that some like 3D based features, such as shape similarity search or 3D pharmacophores, that's on our roadmap to integrate with SynthonGPT. However, this is not possible right now. So far, we have just 2D substructure search. Okay, and if this is all, if those are all the comments, then thanks again for your attention, and see you on our next webinar, which will be announced soon. If you have any more questions, comments, or want to try SynthonGPT, you can go to our website or ask us on info@deepmedchem.com or use a direct message on LinkedIn if you wish. Have a nice day. Bye.